The global economy is currently undergoing the greatest change since the Industrial Revolution. In order to remain internationally competitive, modern factories must be as flexible as possible and highly digitized. The smart networking of people, machines and industrial processes is the ticket to a new age. Industry 4.0. Reutlingen in Baden-Württemberg has one of the most modern semiconductor factories in Germany. With meticulous care and highly automated, the soccer field-sized cleanroom produces around 1 billion micromechanical sensors per year, which are used in cars and smartphones. The structures in the nanometer range are applied to silicon wafers. Silicon is a semiconductor, but what is it good for?
Semiconductors. We actually have three terms here in the group: the senses of a device, the brain of a device, and the muscles. We are currently the global leader. We've produced over 10 billion of these micromechanical sensors to date, both for automotive and consumer electronics.
In the so-called wafer fab, the future is being built.
In the field of electric driving, autonomous driving, networking, but also in the consumer sector, we are continuously developing sensor technology.
In the sterile, futuristic tech world of the plant in Reutlingen, as the internal code of the facility goes, it feels more like being in a space station than in a factory. Every square centimetre of the 23,400 square metre area is designed across several floors. A tremendous effort to enable precision in the tiniest of spaces.
We model very small structures. The smallest are about 1,000 times smaller than a human hair.
What is being built here in Reutlingen is found in countless products spread all over the world. In vehicles, mobile phones, in just about everything that requires electronic control. Klaus Meder is chairman of the Automotive and Electronics Division.
In Reutlingen, we manufacture semiconductors and sensors mainly for the automotive industry, but also for the consumer sector and control units. Approximately half of all modern smartphones that you can buy on the market today contain sensors from the Reutlingen site, such as sensors that measure rotation rate, acceleration or pressure differences, and in every fitness tracker that we are likely to have today.
The group, which is best known to most people for domestic engineering, is also active in less visible areas of modern life. However, this would not be possible without a widely used chemical substance. The technical plant manager, Patrick Leinenbach, is responsible for semiconductor manufacturing at Bosch.
The base material for our manufacturing processes is silicon. Silicon is a so-called semiconductor. It has both insulating and conductive properties. You can actually think of it as sand.
Besides impurities, sand consists mainly of silicon. However, only pure silicon is used for chip production.
And then this silicon is extracted from so-called ingots, such rods. This rod is made of high-purity, high-density silicon material. It weighs about 10 kilos. From that, our silicon wafers are cut. We don't produce all this here, but we buy these so-called wafers, which are made of sand.
Experts refer to one type of chip produced here as MEMS, micro-electromechanical sensors. Jens Fabrowski is the divisional director responsible for semiconductors.
Semiconductors are the little black bugs we know from electronics, and they are really very small. Our smallest ones have an edge length of 1 millimeter. The bigger ones are as big as a thumbnail, and that's where we put our circuits. There's silicon in there, all the intelligence is in there, miniaturized and wrapped in plastic with small contacts. The semiconductor scale is the measure of how many functions I can fit into a single component. The smaller the semiconductor scale is, the narrower the tracks and the layers are, the more functions I can pack into one component of the same square millimeter size.
To get this intelligence into the tiny parts, around 3,500 employees work in Reutlingen in 3 shifts. The real writing work on the silicon wafers is done by machines. Here, more than 15,000 of them. The wafer fab is a single highly automated machine that produces over 4 million individual parts a day. In order to maintain an overview here, computer-aided production control is required. Stefanie Hessel is responsible for this. Her team ensures that no errors occur during the thousands of strictly regulated parallel processes.
The production control is responsible for ensuring that the wafers move ideally through the production process. A wafer is a silicon plate which is processed by us and which runs through up to 1,000 process steps in succession. The movement of the wafer is partly ensured by automation. This means that robot transport systems move the wafers through production. The purpose of automation here is that each wafer must know where it's moving to next, what the next process step is that it will go through. That's where software, a planning system, supports us because it's such a complex situation. We have up to 70,000 wafers in stock, which move around here for up to 3 months and see the same equipment and process steps over and over again.
But why is it necessary for the highly sensitive wafers to go through the same processing steps over and over again for months? Bekir Zermacic, who heads an engineering department, can answer this question best.
You can compare this very well to designing and building a house. You build the house on one level, create different rooms, and then go up to the first floor, to the second floor, then to the third floor. With the chip, it's very similar. On one level, you realize different building elements. And in order to make the most out of the chip space that you have on the wafer, you have to move up. This means that the different other levels then happen on the different other floors. The process sequences are repeated in the same way as in house building. There are crafts that do plastering or install cables. This takes place in every room, and that's what we do on the wafer surface in the same way from level to level in recurring cycles.
To be able to produce houses on a micro scale, Bosch employees in the wafer fab, the clean room of the highest category, have to follow a strict procedure every time. No one enters the facility in normal clothing. Washing hands and walking over several adhesive mats on the floor is mandatory to get into the changing room in the first place. And that's where the actual clean room clothing is waiting. Putting on the clothes follows a strict procedure, from top to bottom. No body hair and only the area of skin around the eyes may remain free. All employees have their own suit.
I'm going into the wafer fab right now, and to do so, I have to cover up completely every time. Firstly with the hood, and then also with the overall. This is a special material that is suitable for clean room use, which emits very few particles and therefore helps us to maintain cleanliness in the clean room.
The final preparations, then a strange machine world waits behind the overpressure airlock, which permanently blows air and therefore possible particles out of the clean room. In the wafer fab, nothing is left to chance. Every installation, every section and every step is precisely planned. In 2010, the group inaugurated its Reutlingen factory for the 200mm wide wafers. This is where the MEMS, often months-long construction process begins.
The raw wafers are ordered here. They come up in this paternoster and are then launched into the system so that the commerce knows exactly which material is coming. This is then booked so that I can put them on the labeler. This is on station E2.
First, each wafer receives an ID. Before the wafers become chips, they first get a chip.
This chip helps us to know where each box is at any moment and which step is planned next. This is an RFID chip that is written virtually and not manually. That means we use it several times. As soon as the box is delivered, the memory is erased and set to 0. As soon as a new batch is launched, like here, it is rewritten with the new batch number. The number of the wafer on the RFID chip remains the same as long as the wafer is here in production. That means it can take from 14 days up to 3 months.
Production time for such a sensor or chip can almost be compared to building a house. There are big differences there too. Am I making a prefabricated house or building brick on brick? In our production, we have different production times depending on the design and on the chip. We're talking about processing times from a few weeks to 2 or 3 months.
Here we can see on a chart what we do all the day in production control. We see what the utilization is, here, for example, in automation. This way we can see where we have to intervene to avoid congestion. This chart shows the utilization in automation over the last 24 hours online from yesterday up until this very moment.
Such a high-tech cleanroom cannot be run in just any old factory. Semiconductor manufacturing has special requirements. Not only the immediate cleanroom environment, but also the building around it must have very specific features. The silicon wafers and their fragile structures are so extremely sensitive that all employees who are in the same building must follow a special routine. Facility manager Karl Schull knows what needs to be considered in the wafer fab.
We have regulations concerning entrance to the building. We're not allowed to enter the building in our regular shoes. Just like the production levels, we also have a range of purity classes. Down here, we come in wearing regular shoes. Then we change into indoor shoes, which I'm wearing now. Then we go one level up. We change from our regular clothes to jogging clothes, which I'm also wearing now. And then another level further up, we put on the cleanroom clothes and enter the cleanroom.
The building has a very specific structure.
Here we see a profile of the entire building with a total of 4 stories. The top story is where the ventilation system with the supply and exhaust air is accommodated. Then there's the floor where all the cleanroom technology and our production facilities are located. Below this floor is a cleanroom sublevel, and the lowest level is the supply level. Here, the entire media supply and the vacuum pumps are located.
And all this is done to create the ideal environment. An important part of the production is the so-called Bosch process. What exactly is that?
It has revolutionized the manufacturing of micromechanical sensors. The key process for manufacturing is the so-called Bosch process, which was developed by us, by our Research and Advanced Development Department in the mid-90s, and was introduced into manufacturing at the end of the 90s. With this process, it's possible to produce certain structures in silicon which then enable us to create sensory abilities. For example, measuring accelerations by juxtaposing 2 plates, by creating thin membranes that can map the corresponding pressures. All this is due to the Bosch process, which was developed by Franz Leimer and Andreas Schilb in the mid-90s. It then received the European Inventor of the Year award, and later it was also awarded the Future Prize by the German federal president as part of the holistic approach to micromechanics.
The structures that are applied to the wafers are so delicate that even a storm outside can lead to production disruptions, or rather, it could.
In principle, the building has two parts, a building within a building. We have one large block, 48 meters wide and 100 meters long, and it's housed in an outer skin that's completely decoupled. That means that the production level sits on top of this. It has a foundation that's 1 meter thick and weighs over 10,000 tons. The roof that hangs above it, which can see up here, is unsupported. That means that all the ventilation technology and cleanroom technology is completely decoupled from the production machines. This ensures that all the vibrations that come into the building from outside are not transmitted to the production systems.
This joint is visible throughout the entire building.
We're now down on the supply level. This is the inner building, as I explained earlier. Down here is the joint that separates it from the rest of the building and runs through all levels. What we see here is the joint that separates the two buildings. If you look at it from the outside, you'd expect a gap of about 5 centimeters, which we filled with silicon. But we didn't, because that would also cause strong coupling again. Under here, there's only bast fiber, which has been sealed so it's compatible for cleanroom use. Down here, this is just a cover. The construction is the same as on the wall. What we have here are two metal plates which can move freely on top of each other in order to have decoupling here as well. Here we're walking past the gallery, where we can see the building's construction stages, and we can have a look at the different levels. Here you can see these circles, the tubes in the floor where the air flows through later. The cleanroom ceiling is supported by the columns, which is then the airflow level. The air flows back up into the cleanroom. It's very loud here, so I have to speak up. In the background we can hear the vacuum pumps from level 1, which create the vacuum for the production systems.
The sophisticated building technology, elaborate in every detail, reflects the precision required for manufacturing semiconductor products. The basic condition for working reliably in the wafer fab is the highly specialized environment. Thomas Richter is responsible for the wafer front end in Reutlingen and knows exactly what challenges the employees from production planning have to overcome. Everything that the systems build is first digitally simulated.
Our manufacturing processes are relatively complex, so the software is used in a particular way. We always have to know where our material is, which processing step it's in, what the next step is to avoid duplication, and we always have to pick up the right material in the right order. This can no longer be done on the production control handout. This requires intelligent software that maps out everything that happens in the real world to a digital twin in a parallel world. Intelligent algorithms are then determined from this. Which material comes next, and what is the next production step.
Each individual wafer contains up to several thousand chips.
We are talking about a complexity of up to 70,000 wafers that are in production here. These 70,000 wafers are moved 24 hours a day, 7 days a week. In order to manage this complexity, you need the tools to do so, because as an ordinary human being, you can simply no longer understand it.
To cope with this complexity, it's best to leave each individual logistical decision to the computer. Therefore, a large part of the production in the RTP1 is fully automated. This robot choreography is directed by IT engineer and automation expert Peter Buzek and his team.
In fact, we as humans usually don't know where the robot will go next. That's also the special thing about automation as we've designed it here. In fact, all decisions about a robot's next destination, i.e. which batch it should take to which plant, are determined in real time.
To ensure that everything runs smoothly, the production control is always close to the action, but only intervenes when necessary.
We use the digital twin to form the condition of the material on the line. Which production step is pending? What is the current state of the system? Which order is the most urgent at the moment? We map all this digitally in software and control our production flow via the software. The software tells the machine which material to take and which steps to produce.
Software sagt der Anlage, bitte nimm dieses Material als nächstes und fertige genau diesen Schritt.
To develop maximum efficiency, two core areas in particular are automated.
On the one hand, automation as we see it in this area here includes the unloading and loading of our wafers from the production lines. On the other hand, it also includes transporting the batches from one station to another.
In this machine choreography, each protagonist has a distinct role. Specialization increases the output.
The production area in our clean room is very expensive. Therefore, we're interested in using this production area as efficiently as possible. In addition, we can realize fantastic solutions through automation, such as this robot booth we can see here. The robot, which is installed in here as a stationary unit, can move batches in a very confined space quickly and precisely from one system to another.
A human being is not suitable for this task.
We can't touch the wafer because we work under clean room conditions. To give you some idea, clean room means it's like looking for a cherry stone in Lake Constance. That's how pure the air in the clean room is. Of course, the human touch, even if they wear gloves, would be rather counterproductive on the wafer. We would apply dirt and structures and destroy the parts. We are here in photolithography, which is basically the heart of our production. Photolithography is an optical imaging process which happens with photosensitive materials. That's why we use yellow light to avoid incorrect exposure. There's the example of building a house when realizing our product. Photolithography provides the building plan for each floor that we build in the house. For each of our products that we manufacture, there's a building plan for each level, up to 36 levels per product. As the heart of the plant, we are in operation 24 hours a day and have the highest output here. Each product passes through this processing station up to 36 times, and the efficiency of our machines is highest when we operate them automatically. You have to imagine a machine in which the wafer is placed. Different chemical layers are applied there which are differently illuminated by photolithography and then etched off. That means you always have a physical and chemical interaction in the machine. During the process, you want to find out whether it will be a good part or a bad part. That means you record all possible machine parameters. Humans are there to fix malfunctions. If everything runs smoothly, we watch what happens. If we have a malfunction somewhere, we're there quickly and can eliminate the error or the shortage with our know-how. The wafers we process in production are not touched by people. We use automatic equipment for this. This is our level of automation. However, we also work in the Industry 4.0 world, and there we're just moving on to the subject of 5G. The robots all move autonomously, which means they are equipped with sensors and monitoring devices. These 4 generations take care of each other. They are all interconnected. They recognize each other, and like at a crossroads in traffic, 2 robots heading for the same destination coordinate their actions. One waits, and the other has right of way. The traffic between humans and robots, for example in the area we're currently in, is regulated quite simply. Humans always have priority. The reason we have 4 different generations of robots is that on the one hand, we have stationary robots that work in specially constructed booths. These are small rooms where we can really make optimal use of the available space. And a stationary robot, which is capable of making really adventurous movements in a very small space and can move batches very quickly, is ideally suited to this purpose.
However, there are 3 robots in Reutlingen that enjoy a very special status.
We named the robots ourselves, of course. They're Eva, Paula and Robert, and there's quite a nice story behind it. The real purpose of naming the robots was to differentiate between them. It is, of course, much easier for us humans to deal with robots if they have human names. The very special thing here is that we named them after the children of Robert Bosch. This is a way for us to make sure that these robots belong to the Robert Bosch family.
Robert Bosch, who founded his workshop for precision mechanics and electrical engineering in neighbouring Stuttgart in 1886, would certainly be proud of his mechanical descendants.
After this quality processing step, the goods move on to the next processing step, which can be diverse. That means I don't know the exact destination. Therefore, the goods are transported via the transport system behind me back to the main aisle and are distributed from there. And every time a batch travels onto a turntable, the decision is, does it go straight into the storage or does it turn off to the next production line? In these situations, decisions are made in real time. The system recalculates which priority is now the important one and which route the batch should take.
While the routes of the individual batches are constantly being recalculated, the direction for further development in Reutlingen is already set.
We are now at a point where we will revolutionize electromobility, where we use so-called silicon carbide, which enables us to produce products that in turn enable our customers to provide electromobility with a longer range, lower losses, and lower energy requirements.
Silicon carbide is the material for the chips of the future. The chemical symbol for it is SiC, or SiC as it's known in the industry. In order to use the semiconductor as desired, so-called ions, positively charged atoms, must be implanted in the in-house particle accelerator.
Ion implantation is one of the most important process steps we have in semiconductor manufacturing. It's very complex. The machines are amongst the most expensive, largest and heaviest machines available in the semiconductor world. This implanter is about the size of a car garage, weighs about 14 tons and is very expensive. The ions are generated at the very back of the machine in the ion source. We then accelerate the ions with very high voltages in a vacuum. The voltages range from several thousand volts up to 1 million volts, and we accelerate these particles to nearly light speed. In other words, to very high energies. At these high energies, we then shoot the particles into the semiconductor material. Of course, the greater the energy, the deeper the particles go into the material. However, we can adjust this very nicely with a lot of effort. What we can also adjust very nicely is the amount, the number of particles we implant, the dose.
The SiC ion implanter has its own separated area.
Here we are at our SiC ion implanter. This is nothing more than a particle accelerator. Since we're working with voltages that are 1,000 times higher than those that come out of our power outlets at home, we have to take certain safety measures.
The white doors are only an external protection, but why all the fuss?
The semiconductor conducts the electric current very slowly at first. With ion implantation, we can specifically introduce foreign substances, so-called dopants, into the semiconductor material. We call this implantation, and it changes the electrical conductivity of the semiconductor drastically. This is the basic prerequisite for ultimately being able to produce electronic components such as transistors or similar things on a semiconductor wafer.
The implanter essentially consists of 2 parts, source and process chamber.
In the machine, we have an ion source. Ions are positively charged atoms. They are accelerated, guided around the corner here, come to the front of the process chamber where they're guided onto the wafer. Here we see the process chamber of our particle accelerator, in which the wafers with our dopants are implanted. To ensure that the ions are free passage when they're accelerated, we use various vacuum pumps to create a high vacuum.
High vacuum. That means around 26,000 particles per cubic centimetre. Sounds like dense air, but it is almost as empty as outer space.
There's a lot of know-how and effort behind it to make sure that the machine does exactly what we want it to do, namely to shoot the right dopant with the right energy in the right amount into the material. The system technicians have to put a lot of effort into keeping the machine running. Ultimately, they also have to create this high vacuum so that the ions can fly freely and are not disturbed by any air molecules. A lot of effort goes into that too.
For everything to run smoothly in the semiconductor factory, the different departments have to be coordinated, knows commercial plant manager Dirk Kress.
We at Bosch manufacture sensors that make things talk, that make things record data, and that ensure the connection within the Internet of Things. We manufacture around the clock, 24/7, so to speak. It's a continuous manufacturing program. The site is open 362 days. We always like to say 24 times 7. We schedule all of these 21 shifts a week completely. In other words, if the gears don't engage properly here, we have a backlog that can hardly be cleared again. So it's very important that all departments, groups and teams work well together and really interlock like a gear wheel system. And then that has to work for 362 days.
Zahnradsystem ineinander greifen und das muss dann 362 Tage drehen.
Teamwork is our core competence. Our slogan here at this location is "We at RTP1." This stands for cooperation between our front-end processes, wafer production, and our test center at the back end. At the moment, this is symbolized by the bridge we're standing on. We employ all sorts of apprentices here, and of course also academics. The site has been providing training here since 1965, almost since the takeover of the site by Bosch. Of course, a lot has changed over the years. New occupations have been added, new training content. The world is changing around Bosch. Bosch is changing itself. Employees play a very important role when it comes to quality. The staff follow the highest standards in order to produce high-quality products every day. Quality is a very important core point. Of course, it is very important that we produce quality, but we also have 100% test coverage to ensure quality.
The enormous effort that is put into the production of the several million MEMS, micro-electromechanical sensors, every day is considered in their various test cycles, which are a science in themselves. Only the dress code is a little more casual.
We have a clean room here too, but the wafers are already fully processed at this point. That means that the clean room standard in this area is no longer as critical as before. Therefore, the covering is not as extreme here either. We only wear face masks, hoods and gloves combined with a clean room gown. At the end of the process chain of 2 to 3 weeks or 2 to 3 months, a final electrical test takes place. That's the equivalent of my final building inspection or acceptance, so to speak. Only when that has been passed and every single chip is judged to be in order, can I then hand over the keys. Just like when you build a new house.
So that the final building acceptance can take place, about half the employees alone are on duty in the test center.
The wafers produced in the wafer fab are delivered here and are measured and tested for function. This means that every wafer produced in the wafer fab has to undergo a quality test. The chips on the wafer are tested 100%. When the wafers are delivered, they are sealed in the wafer box. The operator or employee who works here is not allowed to touch the wafers. We only have carriers or boxes that we transport, which we load into machines. We are not allowed to touch the wafers at all. During measuring, the chips are contacted with such measuring needles. The measuring needle is about the size of a human hair with a diameter of 75 micrometers. After loading, the additional hardware must be inserted into the machine to ensure that the correct contact unit for the particular type is installed. The machine uses a camera system to focus on the needle tips and then knows where the needle tips are and positions the wafer directly under the needle tip so it will hit the pad. Due to the variety of products we're testing here, a wafer, or map, has different numbers of chips on the wafer. Depending on the function, the chip is larger or smaller. It means that we have a few hundred chips to several thousand chips on one wafer, which we have to contact because we're doing a 100% test. On the electronic wafer map, the employee can see which chip has been measured and which one still has to be measured. You can also see which measured chips were good and which were conspicuous. The conspicuous chips are not processed any further. When the wafer measurement is finished, when the complete wafer has been measured, the data is sent to our system, stored, and is sent to the next quality gate, where the visual inspection of the chips takes place.
The electromagnetic measurement is only the first part of the control stage. Just as there are possible errors that can be measured but not seen, there are also possible errors that get through the measurement but are detectable and therefore avoidable. Visual inspection is the domain of process engineer Heiko Schäfer. It is his responsibility to make sure the visual inspection finds any final defects that may have sneaked through. Fortunately, however, not with the naked eye. Only a special camera can do this. For this task, he and his team also have highly automated equipment at their disposal.
We're here at the visual inspection, where we visually inspect all wafers and all chips 100% to find any anomalies that are still on the wafer.
What does visual inspection mean exactly?
We look at the chips which were found to be positive during measurement to make sure there are no more anomalies. The chip can then be delivered in top quality. Here you can see how the camera runs over the wafer chip by chip and scans it, and immediately carries out an evaluation of whether the chip is still good. An anomaly can be something like a conductor path, which is perhaps not completely distinctive, but enough for an electrical measurement. This can lead to problems in the lifetime of the chip. Such irregularities are found here, and they result in these chips not being released for delivery. We have systems that perform the visual inspection automatically and are trained by us. This enables us to carry out an image-to-image comparison with a very good and optimally trained reference image so that the quality is high throughout the entire product line.
Yet another technology is used.
Our group has set itself the goal of producing or equipping all our products with artificial intelligence in the next decade. I always explain this to myself by saying that it's the reproduction of intelligent action by algorithms. And that's what we're doing here. We have products that contain artificial intelligence. But we also have products that are produced with artificial intelligence itself. I'm using an algorithm to teach a system to get better. Normally, I have a good part and a bad part compared to the visual inspections, and my program compares the good part with the bad part. However, I can also teach the program to learn what a good part is. That means I can make programs learn, something which will then have uses in autonomous driving, for example. Used here in our production, this means that we make processes that are monotonous, that are prone to errors, using individual systems that simply improve themselves, for instance in planning or in optical controls. Imagine that you have to search for and evaluate anomalies in images for 8 hours a day. At some point, this becomes very monotonous. That's why we want to relieve the employees by using artificial intelligence. Humans must train artificial intelligence in this area. That means we have to know about the complex algorithms we use there. We have to provide these sample images and evaluate them to ensure the algorithms have their correct function at the end.
Depending on the application, the chips on the wafers are finally built and successfully tested after weeks or even months. Then there's nothing to do but wait. The finished batches finally end up in the so-called die bank. Here they are stored under special conditions and wait to be used as sensory organs or as the brain of a device. Engineer Matthias Pauli is the man in charge of die bank.
The RTPI-1 die bank is our strategic warehouse for finished and pre-measured wafers. Die bank comes from English and means nothing other than wafer storage.
And what exactly characterizes a strategic warehouse?
Strategic warehouse means that if the customer places an order with us today and has a desired date in 6 weeks, then we would have no chance of meeting that date if we started to manufacture the wafers today. Our goal is to have the wafers fully processed and pre-measured in stock so that we can ship the wafers to the next 2 stations, assembly and final test, on the same day and meet the customer's desired date.
The wafers are not touched by human hands until they're removed from storage.
Roughly speaking, we have 6,000 batches stored here, all of which are logged systematically. This means that you don't have to search here. You can find out directly via the system where the goods are located that are needed, and then go straight to them and take them out of storage.
How much time the wafers, with all kinds of chip kits, actually spend here varies greatly.
Usually the storage period is 2 weeks. However, we also have special cases, such as final stockpiling of parts that are no longer produced today. They are also stored here, and we can store them for up to 10 years under these nitrogen conditions. If it goes beyond the 10 years, special requalification tests must be carried out. If they're successful, we can also outsource wafers that have been stored for more than 10 years. We don't store the wafers in normal air, but also in nitrogen, in clean rooms class 1000. That's because the wafer surfaces are still freely accessible and are very sensitive to corrosion or even damage. And this nitrogen rinsing makes sure that the wafer surface remains unchanged. In order to save nitrogen, a major issue here, we have installed a special control system. If a certain humidity value is exceeded, the nitrogen control is triggered and blows out the humid air.
A major issue is not only the desire to save nitrogen, but also the safety of the employees. After all, nitrogen is only harmless in the air if it doesn't exceed a certain proportion.
The level of oxygen content is monitored constantly. If it were to drop below a certain level, an alarm would be triggered here, which would first be processed by the supervisors. A dangerous situation would immediately trigger an evacuation alarm.
Fortunately, this has never happened before, except for practice purposes.
More than 4 million of these end products leave our plant every day, all of which were manufactured and tested here in Reutlingen.
The traditional German company is optimistic about the future. A great deal of know-how and effort will therefore continue to be invested in these tiny but smart building blocks of our everyday technological life. The RTP1 in Reutlingen, a true mega plant in a class of its own.